Hello, everyone, and welcome back to my channel. So today I start recording the lecture sessions on the Math 407 course, Introduction to Game Theory. So this is the outline of the presentation. I'll mainly introduce game theory. I'll talk about the definition of rationality, utility maximization, what is intelligence? What is domination? I'll give some simple examples and I'll finish with a small summary. So first of all, what is game theory? Game theory is the form of study of conflict and cooperation. Game theoretic concepts apply whenever the actions of several agents are interdependent. And of course, these agents may be individuals, groups, firms, or any combination of these. In game theory, we assume that decision agents are rational and intelligent. So, in fact, the concepts of game theory provide what is called language to formulate structure and analyze and understand strategic scenarios. So, in general, game theory, as an introduction, provides a general mathematical framework or general mathematical techniques for analyzing situation in which two or more individuals make decisions that will influence one other's welfare. So a little bit of history about game theory. The earliest example of a formal game theoretic analysis is the study of duopoly by Antoine Cournot in 1838. And later on, the mathematicians Ernest Zermelo in 1913 and Emile Borel in 1921 suggested the formal theory of games. And this theory developed later by John van Neumann, 1928, in the famous theory of power games. Game theory was, in fact, established as a field on its own after the publication of the monumental volume theory of games and economic behavior by John van Neumann and the economist Oscar Morgenstern in 1944. And in fact, this book still provides much of the basic technology, which is still in use today. What is a game? What do we call players? What is rationality? So in general, a game refers to any social situation involving two or more individuals. And the individuals involved in the game are called usually players. And there are two basic assumptions that game theorists generally make about players. First of all, assumption one, game players are assumed to be rational. And assumption two, game players are assumed to be intelligent. And each of these adjectives, in fact, require some explanation from a technical point of view. So what is rationality, first of all? What is a rational player? A decision maker is rational if he makes decisions consistently in pursuit of his own objectives. So in game theory, we assume that each player's objective is to maximize the expected value of his own payoff. And the player's payoff is measured in some utility scale. This idea, in fact, goes back to Bernoulli, 1738, but the modern justification is due to John van Neumann and Oscar Morgenstern in their famous book. So what is utility compared to money? Maximizing utility is not necessarily the same as maximizing the monetary payoff. And utility values are not necessarily measured in dollars and cents. So a risk-averse individual may get more incremental utility from an extra dollar when he is poor than he would get from the same dollar when he is rich. And this could be modeled by some utility function like q of x equals 1 minus e to the power minus cx for some number c that represents the risk aversion index. What is expected utility? A payoff or utility, in fact, reflects the desirability of an outcome to a player for whatever reason. And if the outcome is random, payoffs are usually weighted using probabilities. And the expected payoff incorporates the player's attitude towards risk. So Ramsey and Savage showed that even when objective probabilities cannot be assigned to some events, a rational decision maker should be able to assess all the subjective probability numbers needed to compute these expected values. And to do so, players need to understand their opponent's decision-making behaviors. And what do we mean by decision? By putting yourself in someone else's shoes, is that each player would try to put himself in the other player's position. So when rational decision makers interact, their decision problems must be analyzed altogether, like a system of equations. And we analyze a game as game theorists or social scientists. Player in the game is assumed to be intelligent. A player is intelligent if he knows everything that we know about the game. And of course, he should be able to make inferences about the situation that we can make. What happens if players are rational but not intelligent? So, for example, in price theory, in economics, we assume that players are rational but not intelligent. In the general equilibrium model of price theory, it is assumed that every individual is a rational utility maximization decision maker, but it's not assumed that individuals understand the whole structure of the model study. So, in price theory, individuals only perceive and respond to some intermediating price signals. And each individual assumes that he can trade arbitrary amounts at these prices, even though there may not be anyone willing to make such trades with him. Uh, Now we will start talking about what we call domination. So strict and weak domination. For each player in a game, the set of decision options, in fact, represent his strategy set. So for each player I, let SI denote his strategy set. So S index IK represent the kth strategy of player I. And sometimes it's possible that some strategy SIK could not possibly be optimal for player I, no matter what his beliefs may be. So in such case, what happens is that the strategy SIK is said to be weakly or strictly dominated. So the strategy SIK is strictly dominated if its utility is strictly less than the utility of any other strategy, SIL, he owns, whatever the other players do. So for some mathematical notation, so let us now assume that the number of players we have within the game is m, and let m index I be the total number of strategies available for player I. So each player I expresses his decision using a vector of mixed strategies, xi, which in fact represents a probability distribution over his set of strategies. So the kth opponent of xi, or the kth component of xi, noted xa, xik, represents the probability of player I to play his kth strategy. So this capital X, in fact, tuple, represents the vector which compiles all the decisions taken by the players, player 1 till player n. And let ui of x be kind of a utility function associated to player I. So from a mathematical point of view, if SIK is strictly dominated, one can write that the utility provided by x when xik is allowed a probability of being played 1 is always strictly less than the outcome u of I provided by capital X when some other different strategy L is played is allowed 100% or 1 unit probability of being played for some L not equal to K. And if this strategy is weakly dominated, if one can say that we have a less or equal sign. So let's take one first example. Here we talk about the famous Flood and Drescher 1950 prisoner's dilemma example. So in this context, after committing crime, two criminals were arrested by the police, and they are being interrogated in two different rooms without any possible communication between them. So the police does not have enough evidence to convict the pair, and each criminal has two possible decision options, either deny, which is symbolized here by D, or confess. And if the two criminals confess, they would serve 2 years in prison. If the 2 criminals deny, they would serve only 1 year in prison. And if one confesses and the other denies, the first would be set free, while the other would serve a 3 years sentence. So this game can be described through the following table, where here we put into matrices the payoffs. So this is what happens when both players confess. They both get -2 and -2 in terms of years in jail. If first player confesses, he gets a 0, while the other player gets 3 years in jail. And this situation is kind of symmetric. If he denies while the second player confesses, first player gets 3 years in jail, while the other player is set free. And if both deny, they get only 1 year in jail. Okay, so this is the Prison's Dilemma original payoff. These are the Prison's Dilemma original payoffs. So one can first of all notice that if the player 1 expects player 2 to confess, he would confess 2. Since -2 is always preferred to -3. So if I'm expecting player 2 to always pray in this column, I would always prefer -2 to -3. Also, if player 1 expects player 2 to deny, he would also confess because he would definitely prefer 0 to -1. Therefore, one can see that whatever is our expectation on players 2 strategic play is we always have C that strictly dominates D, which means confessing is always better than denying. So one can say that strategy D is strictly dominated by C for both players because the game is symmetric. So one can notice also that this situation will end up with, which is having this kind of equilibrium where both players confess, is not the best situation. And we've seen in class how this could be changed if we could introduce some kind of agreement with communication among players. Okay. So one other extra mile we can go through here, how can one modify this game such that the criminals would always deny? Okay. And one of the answers would be to introduce communication, for instance. So the second game we played also is the grade game. And here in this context, without showing our neighbor what we were doing, we were asked to write down on a form either the letter alpha or the letter beta. And we thought of it as a grade bit. And we randomly paired students. And none of the players is allowed to know or knows with whom he's going to be paired. And this is how the grades would end up to be assigned for the course. So we said if you put alpha and your pair puts beta, then you will get A and he or she will get C. And if both you put alpha, if both of you and your pair put alpha, then you both get B minus. If you put beta and your pair puts alpha, you get C, he or she gets A. And if both put beta, then you both end up with a B plus grade. So the question we were asked, what strategy should a rational person choose in the grade game? And these are the game payoffs. So this is me playing, this is my pair, this is what we get if both play alpha, this is what we get if both play beta, and this is the situation where I play beta, my pair plays alpha, I get C, he gets A, and it's kind of symmetric. When he plays beta and play alpha, I get A, he gets C. So one also can notice that if I expect my pair to choose alpha, I would always choose alpha because I definitely prefer B minus to C. And also, if I expect my player to play beta, I will always prefer A to B plus. I will always play alpha. So in this context, whatever is my expectation on whom I'm going to be paired with and whatever I'm going to expect from him, I will always prefer alpha to beta. So playing alpha strictly dominates beta. Okay, and of course we notice the same thing, the same pattern which happened with the prisoner's dilemma is that The B minus B minus situation where we both end up choosing alpha is not like the socially wise situation we should end up with. Okay, and we repeated the game, we played it again, and we tried to settle some kind of agreement among players. And we've seen that still 1/3 of the players deviate from the strategy they played with because they were tempted by the possibility of being paired with another beta, which he or she would change his mind and get a B plus. Okay, so finally, some summary on what we were exposed to in this part of the lecture. So we said that game theory is the analysis of conflicts and cooperation between different agents, and the agent's actions and the payoffs are interdependent. And game theory assumes that there's a rational intelligence, and we should never choose dominated. By dominated here, strictly dominated strategy. And there is a kind of paradox we discovered. If we are all being rational and intelligent, like in the prisoner's dilemma or the integrate game, we might not be able to reach the best situation as individuals or as a community. So thank you everyone for following, and we'll continue with the next lectures.